Okay, so I'm going to start with this talk about interstellar visitors. And when I'm talking about interstellar visitors, I don't mean that type, not the ones of the third kind. Pinched that from the movie. What I'm actually going to be talking about is objects that have been detected that have come into our solar system, and that we've got very strong reasons to believe that they didn't originate in our solar system, so they are interstellar origins. The first one has this very unpronounceable looking name. It's actually Oumuamua, which sounds like I'm making farm animal noises, but it's actually a Hawaiian god of some description. They're beginning to have to scrape around for different names for objects, but they've chosen Oumuamua for this particular very strange object that came into our solar system. It was discovered in 2017, and hence it gets the designation 1I for the first interstellar object /2017 U1. And if you know how to decode the U1, you can work out what date it was first discovered in 2017. The image of it on the right is not very inspiring. It's the little white dot, and the moving streaks are stars, because they were tracking the object, and therefore the stars were trailing across the imaging plate due to the really quite rapid movement across the sky of Oumuamua. It was detected just 33 million kilometers from the Earth, so that's quite a long way. It's a lot further away than the moon. It's more than 10 times further away than the moon is from the Earth. But the slightly worrying fact about it was that when we detected it, it was already leaving the solar system on its outbound trajectory. So it had entered the solar system and flown past the sun and was on its way out, and it had achieved all of that without anybody spotting it. And we're always worried when we find that we pick up objects like that, because we're supposed to have this asteroid detecting space guard system that's looking for dangerous objects that might collide with the Earth. And if this had been on a collision course with the Earth, the first we would have known about it was as it entered the Earth's atmosphere. Far too late to do anything at all. So this was the trajectory that it was on, and we've backtracked from the orbital mechanics of it where it must have been. So the discovery was after perihelion, the closest point to the sun there, in September of 2017, and we tracked it all along the outbound track over to the side there. These dates are in American date format here. I apologize for that. So 9/30 is the 30th of September. So you can see it came in from up at the top there, entering the solar system sometime in May, and zipped through closer to the sun than the orbit of Mercury, and then passed by out, crossing the orbits of Venus and the Earth again on the way out. But you've got to try and imagine this in 3D, because it wasn't traveling in the same flat plane as all of the others. So the entry angle was a very high above the plane of the solar system, and it dived down through, looped underneath the sun, and then climbed back out the other way. It's perhaps shown better in this wider view diagram. So you can imagine the plane of the solar system there with Jupiter, Saturn, Uranus and Neptune's orbits shown distinctly, and Oumuamua diving in, ducking underneath the sun and coming hurling back out of the top. And it's on an orbit that we call a hyperbolic orbit. Orbits of the planets are typically elliptical, usually nearly circular, so they have a low eccentricity. If it was a perfect circle, the eccentricity would be 0. If the eccentricity goes all the way up to 1, at which point the orbit ceases to be an ellipse, and becomes an open curve called a parabola. And if it goes beyond 1, then it's a very open curve, which looks more like it's coming in and going out at a right angle in this diagram, only it looks curved near this very center. The outer arms look almost like straight lines, and indeed that's approximately right, and that's called a hyperbola. So we've got a little animation. I hope that this will come through. Here we go. So it comes in, dives underneath the sun, just misses the Earth and goes back out on a slightly flatter, lower trajectory. So quite an interesting path. Clearly missed us, but had a fairly close approach to Mercury on the way there, and not that far from the Earth on its departure. Now, the interesting thing about this, apart from the very unusual trajectory, was when it was studied, they looked at the light curve of it, the amount of light, the brightness, and it seemed to be exhibiting this rather curious cyclic pattern as shown in the animated chart on the right, where it would dip down to a minimum and then climb again. And the simulation to produce that sort of light curve is as shown in the animation on the left, where you have a very long, thin object tumbling in multiple rotation axes. So it's producing sometimes a very, very narrow aspect, looks very faint when it's doing that, and at other times a much wider aspect, which means that it reflects more light our way, hence the rather peculiar looking light curve. And so the artist's impression that I really like, that was drawn up by a NASA artist to show what it might look like, was this: a very long, thin chunk of fairly shiny material, a great elongated shape, 5 times longer than it is wide, and very unusual. I mean, a lot of asteroids are roughly potato shaped, as we call them. They don't have enough gravity to overcome the strength of the materials and pull themselves into a sphere, which most planets do by the ratio of the strength of gravity to the strength of the materials, and of course a bit of heating in the core from trapped radioactivity and so on. But of course a small object like this is frozen up solid, doesn't have a liquid core, and doesn't have very much gravity of its own either. But soon after they'd worked out that it was weird in this particular way of being 5 times longer than it is wide, the next discovery was that it wasn't behaving itself, in that it didn't seem to be following Kepler's laws of planetary motion, or indeed Newton's laws of movement and gravity. And what I mean by that is that it was leaving the solar system and it was accelerating as it was leaving. Now, normally things will slow down as they move away from the sun, because the gravity of the sun is pulling back on them, so they'll be accelerate as they fall in and then decelerate as they rise back out of the gravity well on the way out of the solar system. But Oumuamua was actually gaining a little bit of acceleration, and this was very peculiar, and it led to speculation that what we were looking at was in fact an alien spacecraft that was taking a powered trajectory and had come in through the solar system and now was firing its thrusters to leave, and thereby not following a Keplerian orbit and free falling under gravity. Well, it's not aliens until it's aliens, as they say. We have no proof of that. In fact, what we think was happening is that it was behaving in a way that we sometimes see with comets, only a rather strange type of comet, this one. We think that it's very shiny, very reflective, and very cold, and it may well have come from one of these dark molecular clouds, like the Barnard Nebula on the right there, where it's not a hole in space, it's not an absence of stars, it's a thick molecular cloud of hydrogen gas and bits of dust that are blocking our line of sight. And they also block the starlight getting into them, so the center of these molecular clouds can be incredibly cold. And what you can have happen is it be cold enough for hydrogen itself to freeze up as hydrogen ice. And if an object had been formed in that way inside one of these cold molecular clouds and then hurled across space, perhaps by a passing star and its gravity, then when it entered the Earth and the Sun's solar system, heat from our sun would start to boil the hydrogen off in the same way that it boils the water off the outside of icy comets. But with comets, we see the water refreeze as the comet's tail is full of little ice particles. That's why it's so easy to spot. But the hydrogen would boil away, and then it would be too warm in the solar system for it to re-solidify, and we wouldn't see it. But the outgassing of all of that hydrogen could provide the extra thrust that seemed to be propelling Oumuamua, making us think that maybe we'd been invaded by aliens for the first time in history. And it might also explain the long, thin shape of this giant hydrogen icicle. Maybe it was broken off some larger object, who knows? But we haven't really seen it up close enough. As I say, we didn't detect it until it was running away. And one of the ideas that has come up recently is to go chase it. Now, the problem is that it's going so fast, it has more than the necessary velocity to escape the sun on its hyperbolic orbit. And to catch up with it, we need a very fast spacecraft, double the speed of the New Horizons probe that took the very quick 8-year trip to Pluto. Now, it's possible that we could do that with a chemical rocket by taking a slingshot around Jupiter and a slingshot right round very, very close into the sun, using a maneuver called the Oberth maneuver. Fire your engines when you're deep in a gravity well. You get a lot more change in velocity, a lot more delta V, as rocket scientists would say, out of it, which can boost your speed. And the other way of doing it would be to use a solar sail, one of these little tiny spacecraft with a huge square mylar reflector sail on it, and shine a laser beam onto that sail powered from the Earth and propel it across space, and that would be able to go much, much faster than the fastest chemical rocket, and would be a very useful, interesting precursor to perhaps a full star shot of sending some probes out to the nearest stars. It would still take us about 25 years to catch Oumuamua because we've given it a head start, and it is going like a bat out of hell. So it's going to be really quite a difficult thing, but it would be an interesting possible chase target for such a technology as one of these laser-powered photonic sails, as they're called. But Oumuamua is not the only visitor to our solar system. There's also 2I, the second one, Borisoff. Now, this looks much more like an ordinary comet in composition. It's imaged on the right there, and you can see the nucleus with a coma around it, and then the more diffuse tail type structure typical of a comet. And this passed the sun in December of 2019, so just 6 months ago now, losing a little bit of mass on the way, and has a nucleus round about 1 kilometre across, 0.5 kilometre to 1.5 kilometres. But it's also travelling very, very fast, not bound to the sun's gravity, and it's got an even more strongly hyperbolic orbit. Oumuamua had an eccentricity factor of 1.2, just enough to make it escape the solar system. Anything over 1 is never coming back. Borisoff is at 3.36, so tremendously fast. And it's going to leave the solar system with an excess velocity of 32 kilometers per second. That's about as fast as we can make a spacecraft leave the Earth's orbit, and they get slowed down a lot by climbing out of the sun's gravity well. Here's the orbits of both Oumuamua in red and Borisoff in yellow. You can see Oumuamua is quite strongly deflected by its travel through the solar system. With an eccentricity of just 1.2, it bent through about a right angle. Borisoff was going so fast that it hardly even noticed that the sun was there. It was already just slightly deflected by it with this very open curve, very high eccentricity, that means. Well, we've also, we think, been hit by a third object that came into our solar system from elsewhere, and this hit the Earth in 2014, January. Came in into the atmosphere and blew up over Papua New Guinea, and that is in fact a photograph of the object blowing up high up in the atmosphere, looking like a tremendous fireball. And because they were managed to take a couple of photographs from different locations and get a 3D trace of the direction of the orbit, they could work out that it was again on a original hyperbolic orbit with an eccentricity of 2.4. So a terrific speed, probably came into the solar system at 43.8 kilometers per second, faster than Oumuamua. It wasn't a very big one, this one, just under a meter in diameter. And again, we didn't see it coming. It came into the Earth's atmosphere and blew up. And that was the first we knew about it. Now, it's possible that some of these sorts of objects come from a region way out beyond the normal definition of the solar system, called the Oort Cloud. We've got a diagram of it on the right, suggested by Dutch astronomer Jan Oort, as the source of a lot of comet-type objects that we see. We see some comets that orbit around in the solar system in a relatively sane and normal way, like Halley's Comet, that comes back every 76 years. But others come in on these orbits that, when we calculate them, they look like parabolic orbits that go out to infinity. And we think that they probably originate out of all of the leftover builders' rubble left well beyond the solar system, all these region of millions and millions of icy comets that are sitting out in this cloud of debris around the solar system and just waiting to get a little nudge to perhaps tip them on a course fall in towards the sun and then be flung out again. And maybe a passing star could do so, because this scale on this diagram is one of those logarithmic ones. Each step is, each 2 steps is 10 times further away. So it's in astronomical units. We're going sort of planets going out to 10 to 30 AU, in fact, for Neptune. And then the Kuiper belt of leftover second asteroid belt, really, leftover bits and pieces, including things like Pluto and Eris and Sedna. And then around about 1,000 to 100,000 AU is the area where we think is the Oort Cloud and all these comets come from. So again, they would get a small perturbation and just be tipped into the solar system. And this is an example of one, Comet 2017 U7, that came into the solar system and actually had a near encounter with Jupiter, so much so that it tipped the orbit into one of these open hyperbolic trajectories. And so this one's never coming back. Jupiter gave it a bit of a slingshot and threw it out of the solar system forever. So that's going to disappear away from our solar system, and who knows, might end up entering some other solar system and be detected by some alien astronomer in a few tens of millions of years' time. Other objects, though, don't get a kick from Jupiter that throws them out. They can be captured by it. And this is BZ509, a 3-kilometre object, also spotted in 2014. And the 2 plates on the right are in the negative, so the little black dot that's helpfully been ringed in yellow is the object concerned, and it's moved between the 2 plates there. And it's going the wrong way round the sun. Almost everything goes the same direction around the sun that we do, the same direction that the sun spins, and that most of the planets spin on their axis, unless they've been tipped upside down, like possibly Venus and Uranus. But BZ509 is in an orbit that takes it just the same period of time to orbit the sun as Jupiter does, 12 years. So it's almost in the same orbit as Jupiter, but it's more elliptical. And you can see that in this diagram. We've got the Earth, Mars, Jupiter with its orbit in white, and the thousands of white dots are the Jovian Trojan asteroids that follow Jupiter around its orbit in 2 giant clusters. They all go the same way round, but BZ509 is going the other way round. And this makes its orbit very, very tricky to describe. If you were sat on Jupiter looking at BZ509, you would see a very peculiar effect. We've got it in profile and in plan view here from the point of view of Jupiter. So in profile at the top there, you can see it does a blue loop above the plane of your orbit and a shorter purple loop below the plane of the orbit. But it's even weirder when you look at the plan view at the bottom there, because Jupiter's orbit is shown in black, and the blue and purple line that is a very strange shape indeed, crosses Jupiter's orbit twice. Once it zips round inside Jupiter, and then it crosses to the outside and does a most of a lap outside. So you'd alternately see it orbiting out beyond you, and then doing another shorter orbit inside of you. So a very curious relationship indeed, especially as it's going the wrong way all at once. So there's a little animation of that here. This is what's happening if you take a sort of view of the solar system with the fixed stars in the background as your fixed reference point. So Jupiter's moving around with all its Jovian Trojan asteroids, and BZ509, well, it's going to make you feel sick if you watch that for very long with them going the wrong way round. And the question is it stable, and is it going to crash? And we think it's been doing it for billions of years. So it's actually in a very long-term stable orbit configuration that's just missing Jupiter, repeatedly swapping from that inside loop to the outside loop from Jupiter's point of view. Very, very curious object indeed.